much better way to start the morning of the last day than with Zvika. And black holes.
Can you hear me? Can you hear me? Excellent. Cool. All right. So good morning, everyone. So I guess in this room, everyone wants cryptography to exist, but for all we know, it could just be impossible. So in this talk, I'm going to talk a little bit about trying to find a physical justification for the existence of cryptography. So there's going to be computer science, there's going to be a little bit of physics, a little bit of philosophy. There's going to be something for everyone to find disagreeable or agreeable. I'll do my best. So let's start at a little bit of a higher level about this idea of trying to justify cryptography using physical phenomena. And let's think about this notion of one-way functions. So these are functions that are easy to compute, but hard to invert. And let's think for a minute what we mean when we say that something is easy or hard. So we have this model of polynomial time computation. But really, this notion of complexity is supposed to capture the amount of physical resources that are needed in order to perform a computational task. So when we say something is hard, we actually want to model a situation where you need to invest a lot of physical resources in order to perform this task. So why do we think that these objects one-way functions exist? So one reason is that there are some mathematical problems that people tried really hard to solve and couldn't solve them. And then we present a candidate for the one-way function, which is related to the hardness of solving this hard problem. For example, factoring. But of course, always in the back of our minds, there's a possibility that we're just being silly, and there is a way to actually solve this problem using little physical resources. So we have to sort of make an assumption. Another approach is to sort of try to witness nature around us and see that there are some processes that seem to be unidirectional. For example, scrambling an egg seems to be an easy thing to do, but unscrambling seems to be pretty hard. So we can just sort of take that as some evidence that one-wayness should exist. But again, maybe there is some silliness here, because maybe there is a way to sort of efficiently unscramble an egg, and we just haven't figured it out. Talk's over. But luckily, so one way to go is to just trust Iftach that there isn't. But actually, there is like a pretty good heuristic method for trying to handle these sort of claims, and this is called science, right? So we don't just sort of make assumptions based on what we see, but rather sort of conduct experiments and make observations, and based on that, try to come up with a model of sort of how the universe behaves, and we call this the laws of nature. And then if we do this, maybe we can sort of derive from the laws of nature some reason why unscrambling is hard. For example, I don't know, the second law of thermodynamics or something like that. So this is sort of another way to try to justify the existence of things like one-way functions. But of course, we need to be careful, because this is not going to be a proof that cryptography or one-way functions exist. So first of all, like, these laws of nature are just a conjecture. Maybe we're just being silly in thinking that the second law of thermodynamics actually works. Maybe our translation from sort of our model of complexity to actual natural resources is wrong. So you can sort of try to think that maybe it's possible to prove that in a classical world, factoring is hard, but maybe in a world where scalable quantum computation is possible, then factoring is easy. So just having a proof that factoring is hard in a classical world is not going to be sort of what we want. Nevertheless, this is sort of a different angle to approach the problem. So it's nice to get some independent evidence from sort of the way that we're used to thinking about it, that cryptography actually exists.
But Zvika, in terms of motivation, right? Suppose that scrambling an egg or breaking a glass is not reversible. Mm-hmm. It's really one way in a useful sense.
Right. So this is a different question, right? Whether you can derive an actual. It's true, right? I mean, there's another step here that I'm not even talking about. How do you actually get, like, how do you model? How do you make a mathematical model that actually gives you the properties of a one-way function, distribution, and so on and so forth, based on this physical process? So I'm not getting into that here at all. However, in the phenomena that I am going to talk about, this is going to come out fairly naturally. So this is actually something nice to keep in mind, that it didn't have to be like that. So the example, so what I want to talk about today is a connection between quantum cryptography and a phenomenon in quantum gravity, black hole radiation. So let's start by introducing you to a black hole. So if you want a more realistic photo, I have one here. So this is the black hole at the center of our galaxy. So this was taken by this Event Horizon telescope. And actually, you don't see the black hole because it's black. So this is the black hole. No, the black hole is in the middle. And what you see is sort of like matter that's sort of circling around the black hole and sort of falling into it. But the black holes that we are going to think about don't have stuff around them. So we're just thinking about like a black hole that exists in empty space. And what do we need to know about black holes? So in the center of a black hole, there's this thing called a singularity. And singularity has very extreme and very concentrated gravity. And it's not known how to do physics when gravity is very extreme and very concentrated. So this is sort of why physicists are trying to work out a theory of quantum gravity. But for now, we don't know how to do sort of good physics in the area of the singularity. So we don't really know what happens there. The other interesting region for our talk is going to be sort of the boundary of the black hole. This is this event horizon. And this is this imaginary line where if you cross it, then you're going to end up in the singularity sooner or later. Now, the event horizon, at least for big black holes, is not an area of a particularly extreme or concentrated gravity. So it should just look like normal space, like space that we know. And unlike areas like the singularity, physicists have really good theories on sort of what happens in regular empty space. Like they know it really well. Like you're not going to imagine how well they know what happens in ordinary space. So there's this quantum field theory that allows to make very, very accurate predictions. Even when there's a little bit of gravity, like on Earth, if you create a vacuum, then they know pretty well what's going on. And when you try to apply these tools to the region of the event horizon, you realize that there's going to be radiation that's going to be emitted from the black hole. So this is called Hawking radiation, and it was, I think, a pretty big surprise when it was discovered in the 70s, I think. For our purposes, we can just think about it as sort of information that's being emitted from the black hole. So I'm just thinking about it as qubits that are sort of being thrown out of the black hole one at a time.
It's energy.
What?
It's energy. It contains energy.
It's a wave function. So it has energy. Yeah, it also has energy. So what's going to happen if you take a black hole and just sort of leave it to be, it's going to start evaporating. So it's going to start emitting radiation, and the radiation is sort of going to accumulate, and the black hole in the end is going to completely evaporate. So it's not clear what happens sort of close to the point where it actually evaporates, when it sort of gets close to like a singularity. But I think they are pretty confident that sort of so long as the black hole is sufficiently large, then the model for this radiation should be correct. That it's what?
Contradictory.
What are the things that are contradicting?
Radiation and the
Oh, yeah. So the radiation comes out, so the black hole becomes smaller and smaller.
okay.
So the amount, so the size of the black hole is determined by its mass. So if you're emitting mass to the outside, then you're going to shrink. It's generated at the event horizon. Actually, if you're an outside observer, then you don't, like, as far as you know, only the event horizon exists. This is some sort of there's some holography thing going on there.
And this radiation is like a particle which breaks into two parts, one falls inside, one goes outside.
So, okay, I'm not an expert on this. So this is a very common analogy. I don't know if it's completely accurate. It's not exactly particles, it's these modes, which are like a superposition of particles. But, you know, this is where I'm putting my hands up. Okay, so this is what happens. And another thing that we know is that, well, okay, so this is related to what people were saying, but I'm just going to think about it as information. Like the information that is emitted is sort of maximally entangled with other information that remains inside the black hole. And this is because sort of vacuum, if you think about sort of empty space in quantum field theory, it's very spatially entangled. Like if you think about an area which is local, then all of the quantum fields in this area are going to be very entangled with each other. So if something pops out, then something else that is entangled needs to go inside.
it's not electromagnetic radiation.
It could be electromagnetic radiation, but it could be other types of particles.
It's every type of particle.
It's everything. Yeah, it's supposed to be everything. Okay. It looks like in the next workshop we need to have a physics talk as well. Okay, yeah. So again, for our purposes, if we're thinking about information theory, then and I'm saying that the outgoing radiation, just thinking about the black hole as throwing out qubits, then for every qubits that you toss out, there's a qubit that remains inside, and these qubits are, let's say, in an EPR state, so 0, 0 plus 1, 1 over square root 2. So I'm going to use this Dirac notation throughout the talk. I hope it's not too intimidating. Okay, so this is sort of what happens, and now let's try to think at the level of the universe. What happens? So we can divide the universe into 3 parts. One is sort of the area that's sort of outside the black hole. So this is contains the radiation from the past. So we're going to call it R. One is the sort of qubit that's being popped at the current time. I'm going to call it B. And there's also the interior of the black hole that we denote by H. HBR is sort of the entire universe. And because the entire universe, it's going to be a pure state. So at the level of the entire universe, there's no such thing as measurement, only unitary evolution. So you can just think about the universe starting at sort of state 0 and evolving according to a known unitary. So supposedly we can know the laws of physics, so we know how things evolve. And then a black hole is created. And because we're dealing with an example where there's nothing else except the black hole, it's just going to start radiating. And again, physicists know of properties that this radiation is supposed to have. But the interesting point comes when you pass the halfway point of the life of the black hole. This is called the page time. And after the page time, something annoying happens. So if you look at a qubit that is emitted after the page time, then it's supposed to have 2 properties. One is that it's supposed to be maximally entangled. So it's supposed to be in an EPR pair with this inside modes. So this is what quantum field theory tells us, that there's supposed to be an inside mode that is maximally entangled with the outgoing radiation. But from entropy considerations, you also can derive that this outgoing radiation needs to be almost maximally entangled with the radiation from the past. So I'm currently not formalizing what it means to be maximally entangled with like sort of a big state, but we're going to get to it in a couple of slides. But the point is that this is a problem because in quantum information, we know that a system cannot be maximally entangled with 2 different systems. So something needs to be explained here. And there's a really nice explanation that has to do with complementarity. So physicists were saying, well, look, if this B is maximally entangled with something here, in something in H, and also with something in R, then actually maybe H and R are really the same system. Maybe it's like sort of the same Hilbert space that manifests itself in 2 different ways, outside and inside. And like if you're outside, then you're going to see what's going on outside. And if you're inside, then you're inside and you cannot sort of see what's happening outside. So maybe it's okay. Maybe it's not really a problem. And I think a lot of people think that this is the way to go. But then in 2013, there was this introduction of this firewall paradox. It's not actually a paradox. It's just a thought experiment that shows that maybe things are more complicated than they thought before. So let's talk about this firewall experiment. So again, this is sort of a thought experiment, and the goal is to try to sort of expose this violation of the monogamy of entanglement in these 2 systems. So we have Alice. Alice is the player, and it sits outside of the black hole. And Alice knows all of the laws of nature. So she knows what is the unitary evolution of the black hole and so on. And notice that we think that the universe works efficiently. So everything, for example, the evolution of the black hole is what we would call sort of polynomial time process. So she can, for example, simulate the black hole on her computer if she wants. So Alice sits outside the black hole, and she captures the sort of the radiation from the past. So she sits there from the beginning of time, and she just collects this information. And then Alice is going to distill the entanglement. Now I'm going to go back to this. What does it mean for B to be maximally entangled with R? It means that there exists, information theoretically, a process that takes R and produces a qubit D such that B and D are an EPR pair, again, like 0, 0 plus 1, 1. So, if you just look at R by itself, then maybe you don't see it immediately, but there is a way to process, there exists a way to process R so as to obtain sort of the entanglement partner of the qubit B. So Alice just sort of finds this D, and then she collects this new outgoing qubit B and checks that indeed BD have entanglement, so that we have the right EPR pair. And then she's going to jump into the black hole to look for the other EPR partner and sort of witness the violation of the monogamy of entanglement. So for complementarity, you hope that R and H are completely separate, but this shows that you can somehow sort of bring them together in a way that's problematic. And the conclusion is that sort of these entangled modes shouldn't be able to exist. So really, the event horizon does not behave like normal empty space like you'd think, but rather there's some high energy barrier that breaks the entanglement. So if there's, in order to be able to make empty space not entangled with each other, you need a high energy barrier. And this is illustrated by this firewall. And this is sort of the conclusion that they had there, that these firewalls should exist. And this is, I think, to some people undesirable, because it seems like we should be able to think about the event horizon area just as normal empty space and applying normal physics there. So this is why it's a paradox, even though it could be the case that really somehow, I don't know, the singularity affects the area of the event horizon and creates a firewall. But there's some just a second, there is some intuition that it shouldn't happen. Yeah.
By firewall, you mean that no information can go in, or
just that, like the area here and the area here are unentangled.
oh, that they're unentangled?
That they're unentangled. Yeah. Yeah. In order for space to be empty, it needs to be like very highly entangled in quantum field theory, as far as I know. Like everything that I say that has to do with physics is like has a disclaimer on it.
So sorry, so you say that they cannot be entangled. How does that relate to Alice being able to jump into the black hole?
She can, but there's not going to be any sort of partner here. The radiation, there's not going to be in these entangled modes.
Okay.
We want to prevent them from existing.
So it's basically saying the previous slide, which says B is entangled with the inside edge. That
Right.
should be false.
They're saying that it couldn't. Yeah, they're saying that there's a reason to believe that it shouldn't happen. And here's a way to prevent it by having this firewall. So maybe these firewalls just exist, but I think some people in the physics community are very highly motivated to find a way out, to sort of make physics work in normal conditions. So like think about event horizon as like space that we know how to analyze and sort of make it so that this is still the case. And what Harlow and Hayden suggested is, what if this distillation process going from R to D is computationally hard? It's computationally intractable. This means that it's going to take Alice a lot of time to actually go from R to D. And in that time, the entangled modes are going to already reach the singularity, or the black hole is already going to evaporate, and you're not going to be able to conduct this experiment. So they show some evidence that indeed this distillation procedure could be, that there could be a case, there could be a setting where such distillation would be an intractable task based on computational considerations. So that's kind of cool, sort of incorporating computer science into the problem. So this is pretty weird when you think about it, right? Like, okay, so this is going to be computationally hard, and therefore, like, you're somehow forcing Alice's hand to not be able to see this violation of monogamy, and somehow this is fine. But I think that maybe it's okay. Maybe this is fine. So you could say, well, this can be computationally intractable, but maybe I'm just going to, I don't know, spend a lot of time or a lot of energy and just run it in parallel for using exponential amount of resources, and then I'm going to be able to do it. But the whole point is that we know that under extreme conditions, like new things happen. Like we don't know how to analyze things where there's like extremely high gravity or extremely high energy. So maybe in order to be able to sort of in order to solve this computational problem in time, you need to, I don't know, create a black hole or do something like this where, you need some other theory. So you're sort of kicking the can down the line and sort of saying in normal conditions, we think that the world should make sense.
Oh, a very silly question. So Alice and her computer are not part of the world.
Are not part of the?
Not part of the universe.
You can think about them as actually being a part of the universe. So, I mean, you can think about this R as starting from it has a very long sort of sequence of zeros, and Alice sits there.
So you're saying by the time Alice distills R,
distills D from R.
The inside particle would have already fallen into the singularity.
Yeah, it comes into the singularity, and then we don't need to handle it. This is quantum gravity, please take over.
But there's also this other issue, right? That inside the black hole, time sort of stops. So from Alice's perspective, the particle actually never falls into singularity, right?
So it actually, so if Alice jumps inside, then actually it does. If you stay outside, and again, actually, I'm not sure what happens if you have an entangled mode that is created at the event horizon, but it is true that for an outside observer, you never see anything that falls actually inside. You're going to see it getting very close and closer to the event horizon, but it never falls inside. And this is sort of the reason why I said that you can actually think, if you're just staying outside, then you can just think about the black hole as only happening at the area of the event horizon, and you don't need to think about the black hole having an interior at all. But you can go inside, and then it does have an interior.
So computationally hard here, there's no asymptotics or anything. It's just a concrete amount of physical time that it takes to it could be
right. So
could it not be very
but
short time?
it's related to the complexity of for example, the entangled modes getting into the singularity or the evaporation of the black hole. So you're actually comparing sort of two processes. One is the distillation time, and the other is the time that it takes nature to sort of cover up for this violation of.
Is it clear the second time is long, not why is it in milliseconds?
So it's not clear, but Harlow and Hayden actually sort of explain why they think so. Okay, I don't remember the numbers, so. It has to do again with the mass of the black hole. So it's some polynomial maybe n to the 1.5 or something like this that it takes the black hole to evaporate. So long as it's longer, n is the mass of the black hole. So yeah, there's going to be some security parameter. Yeah, but look, if the black hole is too small, then again we don't know how to say it. So this is it's very easy to escape, right? Whenever things become tractable, then we know that we can't solve. So I mean, whenever things become small, then we know that we don't have the right theory. So
actually, to do this thought experiment, Alice has to jump into the black hole.
Right, she needs to jump inside.
The black hole is too small; you cannot even jump into it.
I have another question. So when Alice jumps into the black hole, does she have to do another the entanglement computation? Or how does she do it?
Right. So actually, this is not. I didn't see this treated in the literature at all. So I think they think that it's not, that it shouldn't be a problem, but I don't know what to say about this.
What was the question?
So how hard is maybe it's hard to actually find the entangled partner, and maybe the hard part is not distilling the D, but rather finding the partner in H.
Everybody's body is in the title, right?
Exactly.
Everybody there. That's the point of the black hole, though. In a whatever.
Yeah. So long as you can observe it, then it's going to be bad enough, right?
All entangled.
Ubish, you were going to say something?
No, I think the point here is that the pair are sitting right at the horizon.
So, but the pair is going to slightly fall into the singularity, right?
Yeah, but you're in that region where things move very slowly.
Right.
You find
no, but if Alice, you're saying that. Oh, I see. You're saying it's going to actually take.
Figured out what would be the distilling qubit for that particular FOB, which is sitting right at the horizon.
Okay. So Umesh was saying, I'm just going to say it for the mic, that things at the horizon move very slowly from the frame of reference of the outside. So it shouldn't be that hard to sort of keep track of where this radiation came from and look for the partner in that area. Okay.
Alice witnesses that Alice will never be able to tell anyone else because Alice.
Right. So it's true, and you can try to say, but so the question is, what do you want physical theory to describe, right? You want to have a theory such that any observer should be able to sort of look at the laws of nature and predict what's going to happen to it, including an observer that sort of falls into it. So you want quantum theory to also be correct, even if you're like one of these adventurous people that falls into the black hole. You shouldn't see something that's non-physical, even if you're not allowed to tell anyone.
How always talk to other people who fell into the black hole.
Also, it's not clear what happens when the black hole evaporates, but okay. So let's be a little bit more concrete about this. I have no idea how much time I have. Not a lot. Okay. About this problem of black hole radiation decoding, or Harlow Hayden decoding, you can call it. So the setup for this problem is sort of the evolution of the universe. So there is some way where this sort of state over these three subsystems H, B, and R gets generated. And again, we think of B as a single qubit. And we have a promise that B and R are entangled. So there exists a possibly inefficient procedure to start from R and derive a qubit D such that BD are an EPR pair. Now, the input to the problem is you get access to the register R, and your goal is to come up with a register D such that B and D are correlated. So you can think about trying to come up with D such that B and D are perfectly entangled. But in order to witness the violation of entanglement, it's sufficient for them to be even somewhat correlated, because the EPR partner of B is going to be fully correlated with it. So it shouldn't be correlated at all with any other with any other subsystem.
Why are we assuming that the EPR partner that's inside is somehow the real one and therefore this one is bad? I mean, why not the other way around? Like maybe the one outside is the real partner and inside is not.
So I think, so you're saying maybe it can be like highly correlated with this one and only slightly correlated with that. So I think that the reason is that you just really believe quantum field theory, and it suggests that these partners should be really, really highly entangled. This is my answer, but again, like all physics question, I have to.
Physics is saying that that should be the case.
I think so. That's the best answer that I can give. So what was shown in prior work? So they were considering sort of just trying to show that something useful can be said about this. So they were considering the case of sort of perfectly recovering the register D, and they showed that this is hard under computational assumptions. So in Harlow Hayden, they assumed that SDK is not in BQP. So some problems in statistical zero knowledge are actually hard for quantum polynomial time, and they get some sort of a worst case hardness. So somehow for every adversary there exists a black hole that it should not be able to decode if we try to interpret it. Aaronson gave an argument that uses injective one-way functions, and so the claim there was average case, but based on sort of more cryptographic assumption, based on average case assumption. And what we do here is sort of, again, study this thing. Yeah.
Just going back, so HH said that if, let's say, factoring is hard, then this recovery is hard.
So if there exists an SDK complete problem that is non-BQP,
it has to be complete.
Oh, it doesn't have to be complete, but if there is a non-complete one, there's also a complete one. Right.
It's not a good one because it's in BQP.
It is in BQP.
Okay, so it's not.
I mean, but if factoring is in BQP, anything holds. But in particular, yeah.
Okay.
Sorry, the model is a little bit confused because you're making computation assumptions. So presumably Alice could be computationally unbounded, right? So far, what you have said does not.
So we are assuming that Alice is computationally bounded. If Alice can use unbounded resources, then again, we don't know what happens, right? If Alice can have like an exponential amount of energy and sort of concentrate it on her computer, then I don't know, maybe she creates a black hole or something else that we don't know how to analyze. so the point here is to think what happens in normal conditions. Like the universe needs to make sense under normal conditions. This is how I think about it.
The universe is computationally feasible.
The universe needs to be computational. No, I mean, it could be the case that you can concentrate a lot of energy in a small point, but then we don't know what happens.
Zvika, but at high level, I should think of this work as like using complexity theory to justify that the physics is okay, that like this problem.
So I think they justify that the physics could be okay, right? Like, I don't know that there is a model that says that it has to be the case that black holes should be created in this way, but you can sort of try to go in the opposite direction and say, well, if we think that nature should make sense, then black holes should be created. Black holes should be created to have this property, and this shows that it is actually possible.
Okay.
And this actually sort of ties to the next point, where we might not just want to be able to show that under some computational assumptions, this problem is hard, but rather if this problem is hard, and if we say, well, this problem needs to be hard for like some sort of physical intuition, then this implies that some computational problem is hard, which is good for us. So in this work, so we give a quantitative definition of this problem, so in previous work it was just defined in a more high-level way without all the parameters, and we give an existential equivalence between the hardness of this black hole radiation decoding problem and this arguably minimal quantum cryptographic object. This goes in both directions. So on one hand, we show that you don't even need to have one-way functions in order to have like hard problems for this hard instances of this radiation decoding. And on the other hand, if radiation decoding is indeed hard, then you get some notion of quantum cryptography. You don't necessarily get one-way functions, but you get this notion that we call that's called EFI, or non-interactive statistically binding commitments. So these BHRD hard states exist if and only if this EFI / non-interactive statistically binding commitment quantum commitments exist. So just to say what this, I'm not sure that I'll even get to it, but let me just say what it is. We're going to hear about it more from Ron later. So EFI just means that there are two distributions over quantum states that are computationally indistinguishable, but are statistically far. And you can actually show that the existence of these things is equivalent to a bunch of quantum cryptography primitives. Again, the one that I'm going to care about here is commitments, but there's also other things, commitments, oblivious transfer, and more. So really, again, so this puts this sort of BHRD problem, at least in this formalism, together with these sort of collection of other cryptographic tasks.
So these EFI, what was known about it before? I mean, you're showing.
This was known before, and we just connected to the black hole stuff.
So that is, applications, like if EFI can be used to do all this, but I mean, in terms of existence, like you're connecting it with the BHRD.
So all these are existentially equivalent. So it's not just that you can use EFI to construct these, you can use them to get EFI.
I think he's asking whether EFI were known to exist, not known to exist, what we believe about EFI.
I was asking.
Okay, so they're weaker than one-way functions. If one-way functions exist, then of course, then EFI exists, because you can even get classical distributions that are statistically far and computationally indistinguishable. I think there's going to be talks about this. So, I mean, anyone can, it's anybody's guess, but I think most people, there are some separations that show that things like EFI and even stronger objects could exist even if one-way functions do not exist. So there are sort of relativized reasons to think that.
Are there physical processes that have been linked with EFI before?
Not that I know of. Okay, so we'll see how far we get. Okay, so let's go back to the definition. I'll try to show you how the connections work in either direction. So I just want to say that we can think sort of, again, there's a reason, there's a again, a parameter of saying how correlated you want your adversary to be with the radiation be. So we can think about sort of an easy variant, which is just to try to find any non-trivial correlation. You can think about a hard variant where you want to really come up with a near EPR correlation between B and D. And again, you can say what's the probability of success. So you want to be able to succeed with non-negligible probability. And this is sort of a harder case which would still be able to violate this firewall scenario. So we might want to be able to prevent this as well.
Question: what is security parameter in a physical?
Right. So I was asked before. I think it should be something like the size of the black hole, like the mass of the black hole when you translate it into.
So using your analogy before, like if there were multiple natures with different size black holes, you are using the same algorithm across all. How much more effort you have to put in? Is that the asymptotics?
Right. So there is a question here about like how to deal with asymptotics, and is it. Right. So is this really like polynomial versus superpolynomial time really the right separation that you want between what is going to be sufficiently intractable in order to prevent this, the physical question? I'm not getting into that now. So it was discussed a little bit in the Harlow Hayden paper, and I'm mentioning it in passing also in this paper, but it's true that you can investigate a lot more on the parameters of this problem. So what we show is that even if only the hard variant is hard, then you get EFI, and if you have EFI, then even the easy variant is easy. And notice that this is an existential equivalence, so it doesn't mean that it's the same system. Like that, if a certain sort of black hole is sort of hard for the hard variant, then it's also hard for the easy variant. But rather, if there exists a black hole for which the hard variant is hard, then you can also think about a black hole where even the easy variant is hard. So this is what we get. So let's try to see the construction. I have like 6 minutes. Which direction do you want to see?
The more interesting one.
Favorite.
So I'm just going to say, so this direction uses commitment. So essentially what would happen is that we're going to generate an EPR pair and just sort of commit to in the R region, we're just going to give a commitment to the sort of the half of the EPR pair. So we start with an EPR pair and commit to this part. And this is sort of inspired by what happened in Harlow Hayden and also in Aaronson. You can think about what happens there as some sort of commitment. But when you try to do it carefully, you see that you need to be careful. And in particular, if you want to really be able to show that even the easy version is hard, then you need to really sort of show that you can use the commitment in such a way, that first of all, it is information theoretically possible to recover, to actually recover the qubit from R, and also that you can use the commitments in order to completely hide what's going on. So actually, what we can show is that if commitments exist, then R and B are computationally indistinguishable from being in tensor product. So even though they're very highly entangled, to any efficient distinguisher, they're going to look seem to be in tensor product. And without further ado, I'm going to move to the other direction. So I want to create an EFI. So I want to create two indistinguishable distributions. And what we do there is actually sort of, even though this BHRD is like a quantum search problem, right? You get a quantum input and you need to come up with your output is a qubit, which has some properties. We show that you can actually find a classical hardcore bit for this, given this problem. And in particular, the construction of the EFI is going to be the following. So you start with, you generate this hard to decode state, right? We start with the assumption that this problem is hard. And then you apply this so-called quantum one-time pad, which I was supposed to explain in the previous slides. If you don't know what it is, it's just a one-time pad, but for quantum qubits. So you apply quantum one-time pad on the qubit B, and then your EPI pair is either going to be like the B and R together with the actual quantum one-time pad that you used, or B and R together with like two random bits that are completely independent of the one-time pad. And what we can show is that, so we call this problem like the super dense decoding problem, because it's related to this notion of super dense coding that you can do with EPR pairs. So, if you have an EPR pair, then, if we have two parties and each one has one of the qubits of an EPR pair, then I can send two classical bits along a communication channel by just sending one qubit. And essentially the way that I'm doing it is by thinking about the two classical bits that I want to encode as a key for a quantum one-time pad. I use it to encrypt. I encrypt my half of the EPR with this quantum one-time pad and send it over. And the point is that if you have the other part of the other half of the EPR pair, then you can actually recover the key for my one-time pad, and this is sort of how the communication channel works. So this is sort of what this problem is sort of aiming at, and what we're showing is that so this super dense coding is actually also it's essentially the same operation that you perform when you're teleporting, when you're doing quantum teleportation of a qubit. So actually what we're showing is that if an adversary manages to sort of solve this super dense decoding problem, then we can actually cheat. So instead of giving it the correct B, we're giving it a half of an EPR pair where we have the other half. And what the adversary actually does, it implicitly teleports the qubit D into our register. So it thinks that it's doing a decoding, but actually it's doing a teleportation. So these two things are actually the same operation. And this is sort of how we get a reduction from sort of solving the super dense decoding problem to actually finding D. So this question?
In the interest of time, I'll ask you.
Sure. Yeah. So I'm just going to sort of wrap up. So this is going to give you an EFI construction based on the easy version of the problem, the hardness of the easy version. If you want to rely on the hardness of the hard version, then you need to do some amplification. There are some questions here. I should also mention that Bouland showed me like a different way to show this reduction, sort of doing a dual construction. So instead of looking at B and R, you're actually thinking about H as some sort of commitment. So there's at least one other nice way of sort of getting the result. It seems, right? Is there a proof? So, there should be in his head. So let me wrap up. So it seems like hard problems come up in nature, and if they're essential, then it's a good evidence that cryptography could exist. So Harlow and Hayden were using computational hardness to try to sort of censor the violation of monogamy, of entanglement. And what we show is that in some way, again, so like I don't want to overhype it. So there's a lot of disclaimers, but in some sense, you can see this. You can see if you believe that this violation of monogamy should be censored, then maybe you should believe that quantum cryptography exists. And you could think about other places where you can try to find phenomena which have similar properties. In particular, so this area of quantum gravity seems to be very heavy in sort of very related to quantum information and maybe computational tasks. So this could be like a good area to sort of try to find interesting connections. Thank you.
How hard is it to verify?
So essentially, you could just measure in this EPR basis. So if you just want to,
so I don't. So if I guess something,
right? You need to be able to do it better than random. So if you take a random thing, then you're going to succeed in probability 1/4, and essentially you can show that anything better than that is going to give you some non-trivial question.
The direction where you assume EFI and show this problem is hard. Is the distribution the same as what you expect to see from actual?
I don't think so. But it could be the case that a black hole creates a I mean, it seems like it has to be a commitment of some sort. So and also, you know, we just assuming that EFI exists, right? EFI can have many different shapes. So if you pick a specific one, like maybe one that's implied by the one-way function that comes from LWE, then maybe it's not what you would expect from a natural process. But I don't know.
Yeah.
You mentioned maximum entanglement with high entropy distributions. Maybe we can get random states also from this.
Right. So there's I think that there are questions about the relation between sort of random quantum objects like random states and random unitaries to black holes. Usually the dynamics of black holes are modeled by a random unitary, which again, this is sort of contradicts the fact that you want it to be an efficient process, but this seems to be good enough for some purposes. So a lot of things that can be sort of investigated in this area.
So I have a question. So do you expect to see, if you want to think about like getting more results in this area, are you thinking of using quantum phenomena to try to prove other things like more stronger cryptographic assumptions?
Yeah, you could. So there's this blog post by Scott Aaronson where he describes a conversation that he had with I think Lenny Susskind and I forget. Oh, this is recorded. I should give credit. And there he sort of suggests that maybe there's this physical duality. It's called ADS-CFT. It's very hyped between things that happen on the boundary of some types of universes and what happens inside. And sort of Scott suggests that maybe this could be some type of homomorphic encryption. So there's this work of Umesh and others that show that actually the translation between the boundary and the bulk and the inside should be computationally hard. So maybe you can think about this like as an encrypted version, like the outside is an encrypted version of what's in the inside. And if you sort of do sort of natural evolution on the outside, then actually you're doing some sort of homomorphic operation on the inside. So this is the craziest example that I currently have, but who knows? Or should we
Any other questions?
I was just going to comment that if really is the case that computational hardness is ingrained, is a physical of nature, that something cannot be shortcut or something, then maybe there's evidence of it outside black holes. Maybe there is better evidence here, right?
Right. Yeah. So this is why do we? So I think what I'm saying, why go to black holes? Maybe you can just I don't know. Doing what do you call it?
Can any of this evidence say something about classical cryptography? Like,
this is a really good question. This is a really good question. Like I don't know. Yeah.
Interesting.
Just a second. So there's a question of what is the classical complexity of solving this radiation? Like, what kind of oracle? Do you need? Oh,
You appear.
What kind of oracle do you need in order to? So this is like my cheat. What kind of oracle do you need in order to? What kind of classical oracle do you need in order to solve this decoding problem? And this is an open question. So maybe
yeah. Let's take the rest of the questions offline. Thank you.